Okay. Let's just um, let me check that the recording is working and stream to YouTube. Yeah. It is streaming. Yeah, and the volume sounds okay. Okay. Anyway, let's get started. Understanding neural networks to the sparse circuits. Okay. We train models to think in simple, more traceable steps so we can better understand how they work. Okay, so it's about training models apparently. Neural networks power today most capable AI systems, but they remain difficult to understand. We don't write these models with explicit step-by-step instructions. Instead, they learn by adjusting billions of internal connections or weights under the master attacks. Oh yeah, that's the obvious thing. I mean, they really need to write this because I feel like a lot of people who are not in AI don't eh, they don't understand that. And even people who are in AI, uh, they don't really think as. And I think there's a lot of people who just think. Oh, sorry, someone is writing on chat. Yeah, I will go to the paper. I just was going to go through the blog first. I mean, if you want, we can just skip to the paper, but I was going to just read the blog first because it's a summary of the thing. Yeah, yeah, makes sense. By the way, for the this might not. I don't know if the chat shows on the. Yeah, it's not showing the recording. For the people who may be watching the recording, I just responding to the card saying that the post is for lay people and the paper might be better. But yeah, okay, let me continue. How do we interpretability? So this is. And so it was essential. Yeah, this is how typical stuff of how interpretability is nice. I am curious about this about how they what they say Mech Interp is about. Nice. Interesting that it say it as completely. Maybe let's talk more about that on the paper, but they say it as completely reverse engineer a model computation because I feel like these days Neil is not very optimistic about that more ambitious view of Mech Interp, and people are thinking of more understand some things about how the model works. Wait. Apart from low-level details or explanations to computers, no longer difficult. Permission component to perform there's networks. Okay, so yeah, this is about training models that are more interpretable. And yeah, I have thoughts about that, but I think it's probably should actually read get to what they are actually doing first. Okay. Previous mechanistic interpretation has stand from there, stand neurons, In this network, each individual neuron is connected to thousands of other neurons. By the way, if people do want me to go to the paper, I can just directly and look at some specific thing. We can do that. I just doing this because I thought it was the best idea. And no, apart from Tekken, nobody else said anything. Most networks perform many distinct functions, making it seemingly impossible to understand. But what if we trained entangled neural networks, with many more networks in which neuron only has a few dozen connections? Huh. I guess this is interesting, and maybe they explain why like, they have some counterpoint to this on the paper, but the thing I would wonder here is how much this tells you about actual networks that are not trained on this way. But at the same time, I mean, we don't know much about models in general. Maybe understanding this, if it turned out that it was very easy to understand this weird sparse kind of network, even if the real networks are very different in some ways, maybe you can learn some interesting things about it, or even like how to make with interpretability methods. Uh, and I will wonder eh, how good you can get it to be. Like if there is some performance, but you can get an interpretable network that is actually like even if it's worse than the others, it's at least somewhat good, and you can use it to. I can do the kind of things we don't have any idea how to write a program to do. Like a lot of things language models do. Even if it turns out that real networks that are not trained networks do things differently, having some example of how some network could do it could be very interesting. But yeah. Mm, anyway, let's keep going. We train language models with a very similar architecture to GPT-2, but yeah, I mean, I guess that they being a transformer, they probably say in the paper. Uh, Other ways to be zeros. Okay. So circuit sparsity. Hmm. Yeah. So, uh, yeah, it's okay. Yeah. By the way, so I'm going to put this so people can see the chat for a moment. Yeah. So Naysay or whatever your name, the username is pronounced, is saying that they are wondering why not use a normal model then do dimensional resolution. Hmm. I mean, that's kind of already. Like, that's kind of already. It's like sparse encoders. I guess sparse encoders are not sparse in these ways, in that you're not doing sparsity in the connections or something. Uh, I I think this might have some advantages in that. If you do something like some dimensionality reduction thing on a real network, you are going to miss things. Like when people do things like sparse encoders, right? Well, that's not really dimensionality reduction. Sometimes they have more dimensions, but yeah, when you do, you are trying to summarize in some way with some method that a network that already exists. You are going to miss things, and we don't have like super good. People are making increasingly better methods, but they are not great methods that don't have a lot of error or of reconstruction error and things like that. Mm, and in this case, you don't know like the sparse representation is actually how the network works. Like it's the full picture in this case. So I could see why it's the case, but also let's see if they say in the paper later, like why are they doing this, and we have some better explanation that my idea for that, for why this is a useful thing to do as opposed to just try to look at actual existing networks. Uh, Stand with the sparse models computation entangle. We consider very simple model behaviors. Oh, hi. Uh, Wait, people feel free to just interrupt me or talk at any point, like a voice chat too. You don't have to just write on text. It's no one is writing, uh, but I'll keep looking at this while you write. Anyway, we wish to measure stand with sparse models compared entangled. Other responsible for its behavior, which we can say, yeah, it's just. So it's not. They are not. Um, they are not training a sparse encoder in the. Yeah, that's also true. Yeah. So first, they are not doing something like sparse encoders to the model. They are training a model that has some sparsity in it already, like in the architecture. But they are just putting weights to zero. But like they are training a sparse model, not taking a trained model and doing sparsity on it. And also, like as Aman said on the chat, uh, uh, yeah, Spurs codes are also not end to end. So you are only doing it on a specific layer. Uh, and yeah, here is like the whole network is sparse now. Because it was trained to be sparse. And this might mean that this probably means that the network is worse than I mean we will see. Well, Uh, this says large sparse models are more capable and interpretable, but I think people were complaining on Twitter about this title, and let's see. That it doesn't actually mean that. Yeah, if you just make models sparse, this actually probability increase. uh,
Yeah,
just
just one thing to add is like why you might want to do this end-to-end sparsity thing is because otherwise like there are so many design choices as to like how you enforce sparsity and like where you do it, like, and like I guess the concern could be that those choices like, might affect like what your sparsity uh, lets you learn. While on the other hand, like if you have a technique which is like more organically sparse, then you might ask the question, okay, like, yeah, you can argue maybe that the sparsity is now learning things based on the data rather than like the kind of arbitrary design choices you make as to like, I'll just train an autoencoder in this layer, or I'll combine these layers to make a transcoder or something.
Yeah, and also like the model is trained with the sparsity, so like you know that the sparse version of the model is the sparse version of the model here is the model, so you know it has all of the thing. You are not missing anything. While on the sparse encoder, if you use the sparse encoder and replace the standard encoder in the layer, you might be in the middle there. You do have reconstruction error, and you might missing some mechanisms that don't are not captured by the sparse encoder well. Yeah. Let's parse muy capable interpreter. Yeah. So let me params. So the bigger are more params, right? And uh, this is pre-training loss. with an interpretability from circuit size.
I guess we need to see how they're measuring this interpretability. Because, I mean, the
Mm,
capability is obvious.
yeah. Yeah, so this is just saying bigger models have lower loss for the same sparsity. I would be interesting if it's actually I'm confused by here they say so it says interpretability is pruned circuit size, but how is that not the same as non-zero params? Like we'll go to the paper and look at that, but yeah, I don't know. Like yeah, yeah, for a first sparse model size, in case of sparsity setting more weights to zero, right? But if this is a sparsity, if they are here measuring, if this is supposed to represent the prune circuit size, I confuse why it's not the same as the non-zero zero params, right? Unless it's this is actually the size of the original circuit, and this is actually, but then it's not never mind. Okay. Let's leave that for later, and we look at it on the paper. Uh, to make this concrete, consider a track where a model train of Python code has to complete a string with the correct type of quote. In Python, hello must end with single quote, and hello must end with double quote. The model can solve this by remembering which quote type upon a string and reproducing at the end. Makes sense. Uh, so they make this graph where it's this is cool. Station on linearity. Yeah, it's really cool if it is like gets you like tiny. Yeah, if you only have a few numbers and they do something interpretable. Uh, I think I need to read the paper first to understand some of the like what they mean. From opinions by residual channels, I guess I mean like the residual strip here is only a few numbers now, so it's or well, not sure. I probably there's some explanation on the paper. That's better than me trying to figure it out. To reverse engineering from the figure. Uh, Uses a LP layer to convert this into one channel that detects any quote, another classifies between single and double quotes. Using attention operation to ignore intervening tokens, find the previous code, and copy its type to the final token, and predict the matching close code. Okay. Wait, just random thought that's related to the current thing. I could try. We are doing this already, but I could try for next week. I might ask Leo Gao if he was also, even after we discuss it along, we could ask Leo to see if he wants to come to the reading group to talk about this. I don't know how much they. Is it open is publishing this okay for them to talk about it? And yeah, he may be busy, but I'm still in his small server that he made. With only the people who passed his test on Eluther. Was funny. I might ask him there or something, or just DM him. Anyway. Yeah, but I wouldn't be surprised if he's not. Yeah, he's too busy to go. But I might as well try. Anyway, let's first try to at least look at it ourselves. So if he does come, we have interesting questions. In our definition, the set connections shown above are sufficient to perform the task. They are also necessary. So yeah, if they remove the rest of the model, the small circuit still works, which that's actually pretty nice because this often is not the case with. I feel this is more unnecessary than it refers to multiplier. Yeah, this is a kind of a more stringent like definition of what a circuit doing a task that what people do with with normal networks, where it's kind of a lot more of a mess. And sometimes you have some circuit that you think does the things, but there's also other circuits that also do the thing. If you delete the current one, it starts, maybe it does it less often, but it still kind of works. And if you remove the entire other parts of the network, or I don't think our current methods are good enough that most of the time it works. For some tiny things like, I don't know, Neil's modular addition paper, or things like that. Yeah, you can just replace in that case that's true, but also it's a tiny model that's just doing a single thing. More complicated behaviors are hard to explain completely. We can still relatively simple parse explanations which are repetitive of model behavior. Current. Oh, someone left. Anyway, yeah. The type of variable called current. One attention operation copies the name of variable into the set token when it's defined. Another letter operation copies the type from the set into a subsequent set using the variable allowing the model to infer the correct token. Oh, that's a neat way of doing things. Yeah. That's a nice way of doing Python stuff. Like the copying current into here, and then yeah, and you have the type here. Okay, no, yeah, maybe people are not understanding, but I think I got it, and it's kind of neat. Yeah, the goal is at least to as an early goal, making a model computation easier to understand, but there's still a long way to go. Sparse models, more front-end models, and the remain interpreted. Largest models, sparse models, behaviors. When we deal with motifs and the more conversation, sparse models, we could develop an understanding of hyper-subject target inferentiation for the models. Yeah, that makes sense. Strat sparse circuits for systems models that study sparse models from scratch. I mean, yes, but This is just going back to sparse autoencoders, right? I guess it's more than sparse encoders. It's again back to the thing that Amal was saying, where is this will be like some you are doing sparsity on the whole thing. I guess you are doing multiple layers. That's also like transcoders and also that. Uh,
Yeah, but I think like even transcoders don't really like look into the like the I mean there's nothing they don't do anything with the attention weights and those things, right? So it's all
yeah,
MLP focused. So maybe you could generalize to like yeah, some other technique.
yeah. I mean, you could
Uh,
also do transcoder with all. There's also you could then do with the entire thing, right?
mhm,
Like do sparse on all the parts. Like you can people do train sparse on the coders on the attention
mhm.
sometimes. Like not usually, but there are a few of them on Neuropedia and things like that. Uh, and like I guess you could do something with all of them, but I don't know. Yeah, so that is true. That's no, I don't think nobody has done that, or maybe someone has, but in some obscure paper that we haven't seen. Uh, so so yeah, it will be. It's a bit different from the things people are doing fast and coding.
Yeah, the other thing
Um,
that I'm curious is like, the interpretations that they have shown, right? Like, I mean, like of the specific circuits, like whatever, like the matching. I mean, I'm curious if that has been like manually done or is that still automated? Because I mean, otherwise, if you scale this up, like
yeah,
let's say even if you could do this, then how do you identify the circuits? Like even if they are sparse, right? Like I mean, doing that manually. I mean, the hope with sparse autoencoders was in a way that they could like help automate some of that, but like it's been tricky, is what it looks like, and so. Yeah.
yeah,
Maybe it's easier if it is manual, but it's probably still not. Sorry, if it is parser, the circuits,
yeah.
maybe it's easier, but it's probably still like non-trivial to like, if you have like a huge network, to do it like well.
Yeah, I think that makes sense. At the same time, like I feel like a lot of methods, like a lot of there are a lot of things you can do with try to do causal inference kind of things, where if you actually have some unit of analysis where, well, not really. I was going to say if you have some set of features that are independently meaningful, you can do uh, things with that. But right, you might still have, even if it's sparse, you can still have polysemanticity on the actual on these sparse ones. So and you probably do have. So yeah, but yeah, I do. Yeah, no, that's the seems the main questions I have from these remaining for the paper of how did they figure out the that. And I guess we can go to the paper and try to see that. And there was something else. Yeah, I also want to figure out uh, what's going on with this graph. Because slightly confusing why they mean how do you measure interpretability here, or if it's just the number of how sparse it is, and then why it's different from the number of zero parameters. But yeah, I don't remember if I had any
I
other.
think paper will define it, hopefully.
Yeah,
Yeah.
I don't remember if there was anything else that I said that I wanted to see on the paper. But let's. Okay, we have seen this. Let's actually go to the paper. Okay, the abstract is probably the same thing that we already read. I'm going to quickly check if there is something new that they didn't mention there. Oh, Amand says on the chat, I'm putting here so people on the video can see that he thinks the paper also mentions something called breaches, sparse approximation array trained dense layer. But yeah, it's hard to know how it's different for. Maybe it's like a sparse encoder, but they mean on the. Well, actually, it's not the same sparsity as in sparse encoder, right? In sparse encoders, you are sparse in the sense that you are trying to reduce the network to a set of a large, actually even bigger than the model, than the original thing. Sometimes set of activations that summarize that are sparsely activated. Well, it's only a few activate on each text, and here you have this is sparse in the meaning of you have few connections between weights, right? Uh, I will see to the bridges part later if that's what they mean. But it seems like a different way, so like there are different kinds of sparsity, right?
Yeah, it does seem different in definition, though I'm not sure. Like
Need
at the end of
to
the day,
never
like
mind.
there is sparsity of some kinds. I'm not sure like how different it is in practice. Uh,
Yeah, I'm not sure how to think about that. I feel like I will need to think about that about a lot more and like how the things relate and how they might be different, right? And yeah, no, but let's see what they say about it anyway first. Uh, we can always ask if Leo does come. We can always ask him how they are different. But let's see if this already is playing on the paper. Anyway, comprehensive superposition. Okay, yeah, first learning about basing with situations of parts and then attempting to understand computations of the model with them basis. However, this approach attains human statistics by abstracting away complex computations that are only partially understood. Yeah, that's what I was saying. May reflect the chosen abstractions in addition to the model's true mechanisms. Here, we introduce a new paradigm with less substantially simpler and more general circuits that we can fully understand even at the lowest levels of abstraction. To do this, we take transformers where the mass majority of weights are zero. Yeah, that's what we are deciding. And then no. For a few pseudo channels, the model squares from distributed constant precision across multiple pseudo channels or using more neurons that is really needed to represent a single content. Yeah, I want to understand this. Like this concept of residual channels in this connection, right? So okay, so in a normal, let me quickly check that they don't actually explain it better somewhere. Yeah, before I try to figure it out myself. I mean, someone else knows like how the what a residual channel means in this context. In that you have normally have the residual stream, and that's what I heard. Uh, what I mean, but I'm less sure of how to think about the residual stream in terms of uh, when you have a lot of zeros. Uh, also, wait. Uh, yeah, wait. Is the sparsity only on the MLP or do they do something with attention? Because we were talking about that earlier, but maybe okay. We enforce sparsity on all weights and biases, we are talking embeddings. Oh, there's also on the attention weights then, right?
yeah, I mean even token embeddings. So
Yeah. So
yeah.
that's Yeah, I kind of. This feels like I need to spend a lot more time thinking about how that even works in terms of what that means in terms of the attention layer. Uh, and not something I'm going to understand like today directly.
Yeah, I mean, I'm not sure like if how do they choose? I mean, is it just like purely random? It could just be like purely random, but I mean, at least I could be wrong, but like right now, my understanding is maybe they just set certain weights to zero, and so
Hmm.
like any linear combination with those sets of weights essentially ends up being zero.
Yeah.
Uh,
So yeah, yeah, they have synopsis. I do wonder if random and the things like do they ensure that each neuron has some connections? Uh, how does that work in terms of attention and like the kind of attention patterns that can be done? And I guess attention patterns are not affected; they are still calculated. They just calculated with less neurons kind of it feels like the concept is simple, but like the actual implications of how the thing works seems like I'm too I'm not awake enough right now to figure it out. I need like spend like a while like going outside and thinking about it for a while instead of trying to read a paper on Discord.
yeah, no, I took a quick look at that appendix 8.1, and there's some like weird things there, I think. Yeah, I mean, so there's, yeah, I think Decker just posted. So there is, apart from weights, they also enforce sparsity on like activations, and like basically at each location, like they only retain like the top K activations, and zeroing out all other activations. So
Oh yeah,
and
but yeah, I think this thing, right? The thing that got put on
yes,
the
yes,
chat.
yes, yes. And this is on top of like the weights, right? So they zero out the weights, and then they also zero out the activations.
Mm,
Uh, and there are some other weird things like they don't use positional embeddings. I don't know why.
mm.
I don't know. Yeah, there seem to be some things which I don't. Yeah, maybe it's well motivated, but it seems a bit arbitrary. They also like learn a separate, or I don't know, they learn or there's something there. There's like a separate, like a bigram matrix that they, I don't know, learn or they maintain. They say that, they don't want like this sparse model to learn like things like bigrams, and so they have a separate matrix for that. Again, I have no idea how that works, but yeah. Yeah, it
Oh,
seems like there are a
that
lot
sounds
of
weird.
small things. Yeah.
uh, uh, yeah, I guess this also seems like uh, there's probably a lot of things on the paper, and we might not be able to like figure out all of this today. But let's try look at it a little more. See what it does. Yeah. So um, anyway, okay, let's continue. So with sparse models, sparse circuits. Okay, let's first. Okay, first the thing. Yeah, interpretability metric. Let's see that. Geometric mean of number edges in the circuit across has created task to make quantitative. Okay, let's read methods from the start. Weight-sparse models. Transform models with the parameter set to zero. They are pre-trained on Python code. Okay, so they are just training on Python. Yeah, probably that also makes things simpler. Correct is simpler than your tasks, where they are forced to choose between one or two compressions. If your idea seems to be the US paper is train some simple models that are easier to understand and we can do science on them instead of trying to understand something that's more like real models. That seems like a good idea. Assess the interpretability of models, we isolate small span circuits, the model serves to perform this using a novel pruning method. Okay, yeah. So they do have some novel pruning methods to that's very automated to actually figure it out. They didn't just manually look at them. I think maybe they did have to manually figure out what the parts mean, but yeah, they have some way of finding circuits. Interpretable models should be easy to untangle. Individual behavior should be implemented by compact standalone circuits. This is not obvious to me, but okay. Like, maybe there is some behavior that happens because a combination of a lot of different circuits that do a lot of complex things, and this is only true of very simple behaviors. And maybe this is also true like on these very small models that don't have like very complicated things going on. So, well, I guess that mean that it will also mean it will be harder to untangle. I don't know. Sparse circuits are defined as a set of nodes connected by edges. Definition of nodes is maximally garbage covers the root and covers away to matrices. So they actually, they define a node to mean an individual neuron, attention pattern, residual channel head, or residual channel right. So yeah, makes sense. An edge then is a non-zero entry in a weight matrix that connects the two nodes. So yeah, basically anything that where you do some operation and you get some vector at the end, nodes are the things you get, and edges are the weights that those vectors get that produce that part of the matrix of the resulting vector. Also, okay, someone found the part about pruning when I was reading that. For each task, we prune the model determine the smallest circuit with achieves a target loss on the task distribution. The target loss is 0.5 everywhere, or we prune by deleting some subset to nodes across all token positions. So they are manipulating the nodes until they trying to keep the same loss. Well, or not less than some target loss anyway. So,
But then that does not, I mean, okay, but then those nodes which are like quote unquote deleted then also have an impact, right?
I think that they're trying to. I think they automatically try to find nodes that which nodes don't reduce the loss too much. Right? Oh, let me. So let me go to the part about pruning. Okay, so they learn a set of masks which they use to gauge the respective node locations. Let's have a step function. Yeah, no idea what that means. We train the mask parameters by using sigmoid derivative superrogated gradient to backpropagate through the whatever that function is. Oh, I do know what the straight through estimation is. I think it's a thing where, well, not that. I think there was a thing where there are some operations that are not differentiable, but you can put them on middle of a neural network, and you can still get a gradient by. There are some that can be estimated as you just skip them in the gradient calculation, and that works. Uh,
Yeah, no, I think for non-differentiable functions, that is an estimator that's used for the gradient. Uh, uh, no, but okay, so but this looks like that they have like this is an automated algorithm for like circuit discovery. I mean, not circuit interpretation, but
yeah,
basically you take a task and then you, I mean, you have like data points for the task, and then you run this optimization to find like the circuit which is, which for which like, for a given level of loss, which minimizes the circuit size in some sense,
yeah.
while keeping the loss above certain level. And then you, I guess, yeah, I mean, then the next thing would be you try to interpret what different nodes in the circuit
I mean, in
actually
the end,
do.
the second part is harder to automate.
Right.
You can probably automate it with something like the way they try to automate labeling sports encoders, which is
Mm.
ask ChatGPT to do it.
Right.
The, the, yeah, the labeling is automated, for example, in Neuronpedia by LLMs
Yeah,
labeling it, but at the same time now there are some people attempting to automate the attribution graph construction, uh, like in the biology of LLMs paper, like
yeah.
constructing those attribution graphs. So like automating supernode clustering and stuff like this. There's attempts at that, which I haven't read yet, and that would be interesting to look into. I can send some, or the one I know about.
If you have some that you want to look at, you can put it on the reading group channel, and I could pick it for next week or whatever.
Yeah, that there is author of that in the Ultra AI Discord, so he could also maybe come and present it
Yeah. Yeah.
if he
Yeah. You
wants. I don't
can.
know.
Yeah. You can ask him, or I can try asking him. I put the channel paper on the channel, and yeah, we can try to find authors. Uh, anyway, yeah. Let's back to it, and I think later out how which papers we want to read and which ones we might get the authors for. Being updated. Okay. So yeah, they are doing some pruning, automated pruning, and they get some circuit. And I guess part of the idea is also so far they might have done, maybe they say something, but this seems simple enough that they might have just figured it out manually what the things mean. Uh, I think this kind of methods, like the reason, part of the reason this doesn't work if you do something like this, but with a sparse encoder, is that the sparse encoder is not a good. Two things. First, the sparse encoder is not that good at reconstruction, so you are going to break things if you try to apply patient sparse encoder. And second, uh, it's also not completely decent tangling the features, such that if you ablate a sparse encoder feature, you might be ablating whatever the true features in some more vague philosophical sense, whatever that means, are. You might be ablating more than one thing, and your casual, you don't have the right basis to do ablations on to disentangle the model nicely. And I guess the idea here is this might be easier here because the model might be more disentangled. Even here, it might not be the case. I will have to think of how much this we actually can be sure that, or how much it will be true for this version of these models, that they are more disentangled and each neuron means a single thing or less things. Uh, Such that you can. yeah, you can really say, I don't know, this is the neuron that represents whatever, and not have that, and not have polysemanticity and things like that. But it's anyway. Also, yeah, we're here. Let's also look at the bridges thing. We train a weight-sparse model against a series of bridges. Maybe with intense sparse model activation was a person layer. Wait, what? Train a weight-sparse model alongside a series of bridges. Maybe with the dense and sparse model activation once per layer. I probably need to go to the.
Yeah, no, they say that it is basically, it does seem very much like a sparse autoencoder. Like if you look at that note they have at the bottom.
Oh, each bridge can be viewed as a sparse encoder where the latent space is the sparse encoder zero relation. Okay. But so they are turning away the sparse model as a series of bridges. But the way the sparse model, so they have a way sparse models and they have some sparse encoders that somehow map from the real model to that one, or is the too much and more compression will be correct associated with the sparse and dense activations. Okay, yeah. To compress this, we use multiple bridge loss terms in addition to non-repetitive loss. Okay, so they're doing a weird thing that also this also seems like it could be its own paper. Like, but so they are they so are they training a new model that has some weird loss that has to have the that has is trying to keep it aligned to the sparse encoder of the original model. Want the weight sparse model to match the smallest computations with the bridges accurate translating between the sparse and depth activations. To compare this, we use a 3 bridge loss terms addition to normal predicted loss. Okay. I feel like this could be its own paper and we could spend an entire day on the reading group like trying to understand these bridges things and talking about what things they might have. And the here is just an appendix for some reason.
That's a cool idea, though.
Yeah, it's
If I get it correctly,
cool idea.
they are training the dense and sparse model at the same time, basically,
Yeah.
with disconnected loss.
It seems like they actually train the dense model first, and then it seems like they freeze it, and then trains the sparse model based on that. Although I'm not
Yes.
totally sure.
Yeah, I think
But
they train sparse encoders. No, yeah, I think they freeze the original model.
then
it's
how
pretty
does
cool.
it differ from normal way?
No, because
When you train-
they have a second model, not just the sparse encoders, that is sparse and has a loss that like they are trying to map the original model into this new sparse model.
So it's not just reconstructing the different MLP layers, for example. It's also like taking account the loss of the whole model on some data set.
Yes,
Okay, that's the difference. Okay.
Yeah.
It's the idea of. Go ahead.
Oh yeah, I was just saying that they are trying to make a new model, sparse model that matches the sparse autoencoder latents on the real model.
Just the idea of like, yeah, keeping the latent spaces aligned with a loss term. Like, do you guys know any like research on that? That seems like a very interesting idea.
I don't know. Maybe.
I mean, there was work. I mean, this is like much older work, but like, like domain adaptation. There's this, I think, cycle GAN and those kind of things. They used to have this thing where like you would align latent space by like adding like a loss term. I can find some specific papers. I'm not even sure if cycle GAN is the right example I have in mind, but there were like some, yeah, there was some work like in aligning latent spaces for like domain adaptation and those kind of things.
I, I feel like this idea is too cool to be an appendix and should be its own paper, and hopefully they'll publish more on that. But yeah. Uh, and
But
then you will have
actually,
citations.
so this bridge, I mean, this bridge has its own set of weights, and like, does it participate in like the feed forward of the sparse model? I mean, I'm a little confused. Like,
Yes. So the bridge, it's they say elsewhere that the bridge is kind of like a sparse encoder, like it's not exactly, but yeah, something like that. And the new model is just trained with a loss. The sparse model is just trained with a loss which includes matching the the, the bridge, right? Yeah, so here we want this weight sparse model to match the dense model's computations, which the bridge is accurately translating between the sparse and dense activations. To accomplish this, we use three bridge loss terms in addition to the normal pre-training loss. So in addition to, so in training a model, sorry. So they are training a sparse model that is trained to have lower loss, whatever the data is, but also at the same time is trained with this bridge loss, which uh, yeah, normalize mean square error. Wait, so is
okay,
this of the H1? This is the residual activations of the models of the dense and the sparse. Uh, what's this function? Bridge encoders. Ah, okay. So they are this is just, if I am reading this correctly, isn't this just they are adding the first one is just they are adding the error of the bridge to the
mm,
to the loss. So it's they're trying to minimize the error of the bridge. I'm curious how they train the bridge. If they train, so yeah, what I'm not sure if they so do they train the bridge first, and the bridge is also frozen, and then they do this, or they are truly training the bridge at the same time? Okay, bridge is just invocation. We multiply the bridge. Oh, as personal state will try to it. Yeah, but well, okay, makes it. But what's the loss for the bridge though?
I mean, it's, I guess, end to end, right? So like all the loss terms, or is it like a separate head? Because if you look at the feed forward, like I mean, I still, I mean, like if I mean, I can understand during training, sure you have this loss, but like during inference, like you basically don't need bridge, right? Like if you're doing only
Yeah,
inference
you
through
don't.
the sparse model, you don't need the bridge weights. Yeah, this is definitely like complicated.
Yeah,
And
I feel like this is a separate paper that has been put in the appendix of this one.
yeah, and if it
And we could,
works, like I would suspect maybe like it doesn't work very well, because if it does work, it does feel like you might even
yeah,
this might be a better
maybe
way
they
to like
put it here because it didn't work very well, and if they had, they
My
would have made its own paper.
I have a kind of hypothesis is that this is like first time after a long time OpenAI released some open paper with some actual details like this. So maybe the people in the interpretability team are like, oh, let's put as much as possible. They finally let us release something, so let's
Oh yeah, maybe.
fit in everything that we're doing.
Yeah, like maybe OpenAI wouldn't have let them publish two papers or something. I don't know how the inside politics of OpenAI works
so
or
they
whatever.
just shoved another paper in the appendix, basically.
This seems like if we don't get Leo to come, we could ask him why they did this.
And he would be
Maybe he
like,
could can't
yeah,
say
I
it, but
cannot
it's
say
okay.
anything, sorry.
I mean, that's okay.
Yeah. Maybe not. Yeah.
I still remember asking him, saying something on Luther, like some speculation about GPT, but about years ago, and he just responds with the with a like a sus emoji that he couldn't say anything, but I was actually right. I think, or at least vaguely right. It was later funny.
Nice.
Yeah, never mind. I am also saying other things that are not actually true, but anyway.
I still kind of struggle to see when they mentioned mean like the pruning algorithm. When they say mean ablated.
Okay. Let's switch a bit to the pruning algorithm thing, and if people still want, we can go back to the other thing. I try to understand the bridge thing again. After.
Or if you want, we can stay at the bridge. Up to
yeah, I don't know. Okay, yeah, better. Let's put it in order. Okay, let's first finish figuring out the bridge. So the main thing I'm
I guess the last paragraph on the page is really interesting to me, at least. It seems like the way they construct a sparse model is by just subtracting two different activations, basically. So like double versus single quote task, like to just get the circuits for that specific task. Although it's kind of not clear to me how they actually sparsify it, though. Like that, is there some cutoff like below which like the weights just get set to zero? It's not really clear.
That's part of the pruning algorithm, no?
Oh yeah, probably. So they do this and then they apply that to the result. Yeah, it makes sense.
Yeah, I don't know. This feels like if people have like taken the first few important papers about something like sports and coders and put them all on the same thing and said, "Here it is."
Or at the beginning, I remember they had something about some threshold where it's set to 0. I forgot how it exactly was.
Oh, yeah, goodbye. Yeah, I'm only saying his point. How to. I don't know how long people want to keep talking about this. I'm fine with keep going if people want. I don't have much else to do today. But maybe later, not that. Well, I don't want a lot longer. But yeah, let's go for a bit. Okay, so let's going back to the bridges so quickly. Okay, yeah, so the guy is doing a diagram of the SD term. I honestly, I was not paying that much attention to that. I don't haven't figured that out. But that's still right. But those terms are still to train the only the train the sparse. Well, you train the sparse model, right? But wait, is so is this SD term? So with the SD term, are you training the original model with that, or are you taking the gradient of that but only updating the first? What I'm not sure is what they train the bridge on, or do they take this? Okay, the bridges have encoders and decoders. Okay. Wait, so do you mean that so these losses are for the bridges and this is for the decoder? Okay, okay. I was understanding it wrong. I thought all these three losses were on the image systems. But here it says we have a KL to train the sparse model to access activations from the DEMS models. Are they counting the bridge as part of the sparse model there, or what? So they train both the sparse model and the bridges on those losses.
So they do train both in parallel?
I'm not sure. That's what Deckard is saying, but yeah, I'm not that confident on Deckard's explanation.
Like
But
they say bridges to convert one kind of activations to the other at various single locations. So it seems like the bridge is not part of the
okay,
sparse
put
model.
them here so
Which
people
was
can see that. So the Deckard's understanding is that the dense model is frozen, but the sparse models and bridges are not. Suppose that or two possible combinations of sparse and dense layers. Wait, what? What does that mean? Put any arbitrary layers. Yeah, I'm not sure I understand that. Yeah.
I think I'm not sure, but I think it means
Go back there.
they want to like swap the sparse. Actually, maybe I'm not sure. But it seems to me like it means that they want to be able to swap any layer of the sparse for the dense and like vice versa.
Mm-hmm.
Mm,
That would make sense, I guess. And vice versa. So they want to translate from dense to sparse and from sparse to dense activations. They want to translate both
It
ways.
seems like there's a loss term for each of those for the bridges. Those are two of the three loss terms for bridges.
And the dimensions of the sparse activations are higher.
Right. The making this. Does the paper write anywhere? I was going back to this section to see if they say something that. Okay, because the spurs where the spurs is the osmosis activations.
Yeah, it makes sense to me. Does it make sense to you?
Yes. We use a normalized MSC terms that trains the bridge encoder to accurately predict the sparse activation from dense ones. Ah. Okay, so this is this also the okay. So yeah, I think they didn't explain it again here, but yeah, I think that does mean this is all. Yeah, the technical side. This is the also the loss for the bridge, right?
It also says we run hybrid forward passes of the sparse and dense models using the bridges to convert one kind of activations to the other at various single locations. So I guess they actually do, even part of the training is swapping layers, seems like.
I don't know. I feel like
Wow.
this is like kind of not very well explained because it's all like they have this whole complicated this kind of a whole paper in like one page and we'll have to see if they put more things about bridges or if people use them or something. I don't know. I mean, maybe the reason this is only an appendix, like we don't know if it's the OpenAI only they only publishing this, so they have to publish all of their stuff, or they try bridges and it didn't work that well. I guess we could. Is this from? Do they have any? Are these for bridges or is this? Like, I wonder if they have any interesting result from the bridge thing. But there is code, yeah. If there is code, then that's nice because people can actually look at it and figure it out how it works. And yeah, hopefully someone will do that. I don't think I will, but if some of you want to actually look at the code and put some explanation somewhere, that would be nice. And I link it on the Discord or whatever if it's well written. But anyway, let's see if there is anything. We will focus on this bridge thing. I'm curious if there is other things we were missing on all of this. Let's look a bit at this results part. Whether sparsity or well, I mean, if people want me to keep looking at the bridges or look at some specific part, just tell me and I can go to there.
I'm
Yeah,
still trying to parse the math behind the bridges, the lost terms.
the code
but
says
up to
the code does not include bridges, which is okay. They have
Okay.
to be about like they have to probably they're probably going to publish a new paper on that, right? Or like what? Like it seems kind of. I mean, maybe it did actually didn't work. Does the paper anywhere have any results from bridges? Maybe it didn't work well, and they just mention it because they spent a lot of time of their lives actually getting the bridges to work, and they didn't actually work that well. And then they just wanted to put that, but mention it, but not. It didn't work well enough to actually, make it a big thing on the paper. I don't know. If we can, I'll maybe they also. I wouldn't be surprised if Leo already or some of the other authors already said something early there. Maybe I
I
could.
like when I'm still looking at the bridges math, like when I look at the LKL, it seems like they compose like so when they go from D to S, they first do the F function. So they first basically translate from dense to sparse, and then they do all the sparse layers until the end. No, wait. Okay. Well, like one thing I'm confused about is, couldn't the FI be at arbitrary, like the translate the bridge basically? Couldn't that happen in arbitrary place? Because when I look at the visualization, they oh no, it's only after the first layer. No, I'm so fucking confused.
At least this is
They
much more fun
no,
than on the reading groups when I'm just reading the paper.
I'm not confused anymore because I read unembedding as embedding. So okay, now I see now. Okay, so now the composition works normally like in math. That made me confused. So they first apply the translation from the dense to the sparse. Then they do all the layers in the sparse model until the end, and then they take the KL and they do the analogous thing for the from sparse to dense, and that's part of the loss function. I guess one thing what I'm confused about is why they first hit for each eye. Oh, okay, I see now. So because they do it for each eye and at each layer eye. So the loss. Okay, I see now. The loss goes for each, like, so like first term is one layer in sparse model translates to bridge, translates through bridge to dense model, and then go to the end of the dense model and take the final output, and then do the KL with the ground truth. And the
And
second one in the sparse model goes 2 times. So sparse model once, one layer, sparse model second layer, then translation to bridge, and then it goes into the dense model, and then it goes through the rest of the dense model, one layer, another layer, another layer,
yeah,
until the end.
so
And
is
then
the
they
yeah. So is this thing that the car draw here, right?
yeah. Oh yeah, he did draw it, right? Yeah, okay. I just grokked it now, so okay.
Bernie,
Okay.
I'm
So that
curious if you understand the first loss term, because it seems like the second two loss terms don't actually depend on the bridge at all. Like FI and GNI are the bridge encoder and decoder, and those are not anywhere in the second two loss terms. It's just about the
they are in the
Yeah.
second to loss term. There is FI that's the first thing that's applied. First FI, then MSI, up to MS on a building when they do the KL.
I see it now. Yeah, you're right.
So the bridge is needed there. Yeah.
No.
Do you
Oh my
understand
god. I go ahead.
what is the first loss term for? Because I think I understand the second two, but I don't understand the first one.
It's just pure translation. It's just the active, so that the activations are aligned. I don't wait. And let me say
No,
that's
the first
mean
loss term
square
is
error.
just you apply the you
Normalized.
take
Okay.
the activations of the yeah, it's just the difference between using the bridge, applying the bridge to the dense model
Oh yeah.
and the activations on the sparse model. So it's just the error of
Yeah.
the bridge basically.
Yeah, how well the bridge reconstructs hidden activations in the second model.
But
Ground
actually
truth,
both, like it's
basically.
both directions. Like it's
Yeah, in both directions.
Yes.
Okay, I think I get it now.
But I'm still not completely sure is okay. So they have these three loss terms. So what are they training with those loss terms? The sparse model or the sparse model and the bridges? And do the bridges? Yeah, basically that. sparse models and
I'm not
bridges.
sure.
Okay. But
I
where
would
do
like
they
to know.
say that? I guess it makes sense because they don't explain otherwise where the how they train the bridges, right? Or maybe they say it earlier or later. But like then this paragraph is kind of weirdly explaining it because they are. Or maybe no, not that.
Wasn't there at the top some training section for the bridges? Maybe not.
Okay. Yeah, but I guess you.
No.
It makes sense. I guess you could train the bridges more like a spouse encoder, but I guess you're not doing that. Then it's not there's not that similar to a spouse encoder because you are not training the construction model on the loss on the original one. Yeah, makes sense. I guess what you do, the way they are not mentioning that, they are not really mentioning this because yeah, in their minds it's the same because if you train in the model, right, if you have the bridges and you freeze the first model, by default what happens if you are using the bridges as some pytorch thing that it gets multiplied by the other thing is that when you do backprop it just gets everything gets updated even if it's not frozen. So by default you will train on the bridges if they are not frozen. So I guess unless they specifically mean they froze these. Yeah, I think it could be more. Okay, we train a Weight-sparse model sales bridges. Okay, yeah, that makes sense. Maybe I'm just being dumb and not reading it well because I had in my mind the previous idea that it's like a sparse encoder which is trained on the thing, and then I was being confused by that. But yeah, it could be trained more precisely. The way it could be trained more precisely is by being open.
like alongside could mean first that first dense model, then the sec. Like, do they do it in parallel or serially? Like, but alongside seems to imply more of the parallel instead of serial.
I think the obvious, like thinking about it, like the obvious thing to do, like the foul thing to do is training at the same time. Because like, if you imagine having like the actual code and having some bridges, right, that you are multiplying by the other thing, right? You're taking the activations and you are doing backprop through everything. By default, when you do backprop on the model, you are also getting the gradient for the bridges, right?
Yeah, okay, that would make sense. Yeah, to do it in serial, that would make it so complicated. Why would they do that?
Unless you specifically freeze them, you are going to also train the bridges. If I'm thinking about this correctly.
But yeah, the gradient would be more warped in some sense. Like since you go since that one lost term goes like from one to the other and so on, it's like that would that would make it confusing.
No, but the thing that I said that you did a sparse model and the bridges it might not work. I was thinking if you like the other option that made some sense was if they train first the bridges and then the sparse and then the sparse model to match the bridge. But I guess it's not obvious to me that couldn't also work, but right. But you could I could imagine training the bridges, making the bridges a sparse atoll sparse encoder, where you train it on reconstruction loss on the actual model, and then you connect it to the other thing. But then you wouldn't call it bridge; it would just be a sparse encoder. So in that sense, that's the way that it's different from sparse encoders. Yeah. Anyway, you are right. I'm not going to try to talk about why my weird confusions make some sense. You're just right. Never mind.
There's a pretty funny paragraph on page 16 where it says they identified a bug, but fixing it reduced performance, so they just left it in and didn't really explain anything about it.
Wait, where?
On page 16.
Okay, let me go to that.
It's the paragraph that starts with at some point.
Anyway, before this, I do think they really should put the code for the bridges somewhere, because if they did, that's very annoying. At some point, we define a booking or L0 scheduling that the method of weights have intended L0 schedule, embedding a basis with. Okay, so they kept the book. Okay, booking or scheduling, that means while your weights have the intended L0 schedule.
They're just like,
OpenAI
oh, it works better.
OpenAI in a nutshell. However, oh, okay. Fixing this
Exactly.
hurts quality
It
in
feels
terms
like all
of
of-
capabilities. And okay, so it's not
learning.
just capabilities, but also interpretability. Okay. That made it better. Okay.
But yeah, so if I
This is the divine intervention.
If I understand
no
the
mistake.
divine intervention correctly, the book is the book that the. What do you mean the DLC? Maybe I'm failing the context on this thing. Okay. Also, yeah. There's some details. We got to the bridge part. I kind of skip and started not reading everything else, and maybe we should read a bit more of the other things. But okay, so they have everything has at least 4 non-zero elements or whatever. Yeah, weights, I guess, values. Yeah. We anneal the L0 linearly, so that the model becomes sparser. I'm not sure what does that mean. So they said the sparsity thing is that they wait. So this is separate for the setting weights to 0 thing, right? This is just the normal, the normal penalty, or what? Yeah, I guess it's not that important. I'm a bit I don't know sure I completely understand what the change in the thing the book this LCD scheduling the book is changing is if it's just the normal thing where you have in the loss you have a term for the for the what was the name of the measure where you have how big the weights are, which just the if it's I don't know if it's the normal thing that there is on all losses or it's the top K thing. Oh, because it's the Weight-sparse model. Wait, no, no. Ah, okay, but
I I gave GPT the question like if they are trained in parallel or not, and it's been thinking for like 2 minutes now.
did you just copy paste the paper into it?
Yeah, but, well, Apple did a PDF. Yeah.
What's famous? Also, they use some weird norm that is not layer norm. Okay. There's so much things on this paper. Like, already getting the normal sparse models to work seems like an insane amount of work. Like, this reminds me of the anthropic of the big anthropic paper with the that we spent 2 days on for the transcoders and all that and the activation circuits. But that one seems a lot longer. This one is similarly complicated, but they have compressed it in a relatively short paper.
I wonder if they like tried simpler versions that just didn't work, so they had to do all these changes. I don't think they read about that. Yeah.
Another thing we could ask if we do it.
Yeah.
Anyway, I am liking it, and I feel like this is the day in one of the days on the reading group since the anthropic paper that we have spent more time actually discussing the paper instead of just reading it and being okay. Part of it is because we don't understand it and we kind of need to figure it out together, but
We train a weight-sparse model Elixir set. Starting with an existing dense model, we train the weight-sparse model jointly with the bridges. Wait, is that House Nation or is that a real quote? Oh, that's if you go at the very top, they say that they start with the existing dense model and train the weight-sparse model jointly with the bridges. Therefore, they do not train it in parallel. They start with existing trained
the
dense model.
has found a phrase where they say we train a weight-sparse model alongside a series of bridges. So yeah, I guess that I guess that
they say both.
I guess this is confirmation that it's also ChatGPT also reads it the way. It's just me that I was being dumb.
Okay.
Anyway, what was I looking at? Oh yeah, here. Yeah, eventually I understand this app stop K thing then, right? Because so my initial idea is you have the model and you put some weights at 0, right? But this sounds like it gradually lowers the weights to 0. Oh no, wait, is the wait, where does this app stop K thing is explained? Okay. Yeah, but okay. Like, but I'm not sure I understand. So when .k methods, you have the sparse to encoder, right? And you take the activations that are most activated and keep those. But in the context of this paper, how and where are they using that?
You mean where they are using the up stop K?
Yes.
There's a diagram of the architecture at page 17.
Maybe I should have read the thing in order.
If you go to page 17, does this diagram answer?
Okay, so this is on the bridges, right? But they don't use on the normal sparse. Do they use stop K in some way in the normal sparse model? That is just not this bridge thing.
Mm-hmm.
Or wait, is the figure for the bridges or just happens to be on the same page as the expression of the bridges? Oh, maybe it's not. Yeah, it might not be because it's on the methods thing. Wait, what? Why is there an upstop K then? I guess it makes sense to put it, but well, some sense, but it seems non like seems like an extra thing that is. Okay, yeah, figure charge very for that. I guess I'm curious if they say why they did the upstop K thing because you don't really need that, right? You could just do the thing where you set weights to 0, or is that
They
like
actually do mention like the weights versus activations trade-off on page 15. They say, here, we find that some amount of activation sparsity helps on top of weight sparsity, but that too much activation sparsity hurts the capabilities interpretability frontier again. We also have some evidence that activation sparsity emerges naturally from weight sparsity. It's interesting.
I confused why they decide to do both instead of writing a paper where they do weight sparsity, showing that, and then doing some other thing where, okay, we also did, we figured out that if you also add activation sparsity on top of it, you get better results. Instead of this feels very much like they just added a lot of things until it started working. Like, it seems like very, like a bit over engineer or something for the, like it probably works better, but I feel like there are multiple separated details that they are just putting together here at the same time, right? Because unless I'm misunderstanding something, you could remove the app stop K thing and still have the sparse model by doing the weight sparsity thing, right?
Yeah, and I think they even say that the weight sparsity creates some activation sparsity. It does kind of feel like they're both pretty, I don't know, novel things, and they don't really explain either of them like in full detail.
Weight sparsity. Okay. So first, first sparsity versus interpretability. Yeah, I feel that this paper has a lot of results, and we spent a lot of time on the bridges, and we haven't even read most of the other things. Uh, so, thing I saw Tom get in and then go out. He's been doing that on the other reading groups. I don't know why, but yeah, never mind. uh, Another aspect of interpretability is feature clarity, which empirically seems closely related to activation sparsity. We find that increasing the weight sparsity naturally increasing residual stream motivations. Uh, wait, yeah, so wait, but okay, but here they're talking a L0. Uh, as referring to the hidden dimension of the model, right? For the number of layers concerned, not the top K thing, unless I misunderstand something and they are the same thing. I'm very confused.
They said for absolute top K, they normally set K to 1/4 of the dimension of whatever the node is. So I think that would be, the number changes based on like where it is. But it's like 75% of basically all activations are just thrown away, like the bottom 75%.
Yeah. Okay. So where do they first start talking about the upstop K and why do they do that? Because okay, so that's activation sparsity. So upstop K is the activation sparsity. But in results, so here they are only talking about weight sparsity, right? They are not mentioning this upstop K thing. But I'm wondering if all of the results also have the upstop K thing for whatever reason, or if they have train models without it and with it and check both, right? Does the thing I'm saying make sense, or I just misunderstanding something? Wait, A1. But it's kind of weird if it's only on the appendix, but okay.
Yeah, there's one occurrence of abs top K outside of appendix, and it's just in a footnote. It is pretty weird that they like. I feel like they should talk about it more.
It's kind of weird that they add a different. They have two kinds of sparsity. They add like a second kind of sparsity to the thing and just didn't mention that in the appendix. Yeah. I think that's true, but then that means I'm confused. So I'm talking about the thing the Corda was saying that the L series for the weight sparsity and upstock is for the sparsity. But then I'm confused. But why this? Let me go to the we were earlier on the part with the book, right? Let me find the text on the channel and go search for it. Right. I guess I'll just search book on the thing. Okay. Why is there L0 scheduling if it's... Yeah, what does it mean scheduling? I will have imagined that people... that you just at the start, before training, set some weights at 0 and that's it. And that is how your architecture work. But this sounds like they have a schedule where they change them to 0 slowly or something, or I just misunderstanding what L0 means, or maybe L0 means something else in this context, and it means like the thing where like normally there is an L0 L1 penalty on the loss, and maybe that means that yeah, there's a thing.
I wish they were more clear. It seems like the L0 thing is only for when they train sparse models from scratch, but it seems like the bridge thing is mostly they're not training sparse models from scratch there. And it seems like, to me, I might be wrong, but it seems like the pruning is used for the like creating sparse model from a dense model. But it seems like they also.
I think the pruning is for getting circuits from a sparse model. The bridge thing is how they are using the bridge and they are training a sparse model that matches a dense model, and they do pruning on the sparse model to find circuits. Like the pruning is something like ACDC or something like that, where they are doing like automated circuit search by doing pruning. It doesn't have to do with the translation part, which is what the training with the bridges we were talking about earlier too, I think. But I think I understand this. I think they are just misexplaining things again. In that, okay, so there is the L0 norm. I'm not sure I understand this, but I think it's okay. So they talk about the L0 norms of the weights, right? Which is just the norm is just, I think, isn't this the square of the weights or something? The square of adding the weights or something like that? And so they are just saying, talking about L0 as a way of saying the weights that there are more weights that are zero, not here. But when they talk about L0 penalty like scheduling elsewhere, they just mean the normal machine learning thing where you add the L0 to the loss. So like as a way to get for models to be like, you know, to not overfit and whatever. And this is just they confusingly use the term for both L0 for both things because it makes sense, but it's kind of a weird way of talking that makes it that, or I'm misunderstanding something, and they are somehow gradually putting the weights to zero, but that will seem less sensical way of doing things. Does that make sense, or I'm saying nonsense?
They define it as total number of non-zero elements in the vectors. In this normal way.
In normal machine learning, there is like such thing as L0 localization, and there is some official, like there is some definition, which is like, I think the square of the sum of the, what's zero norm? And just that the L0 norm is, it's like it's a vector norms, like
You mean some of the magnitudes of the vectors?
Some of the magnitudes, right? So I think
isn't that L1 norm and this is L0 norm?
Yeah, I don't remember what the L0 norm is. But L0 norm
seems to be total number of non-zero elements in a vector, while the L1 norm is the square of the magnitude. So I guess that would make sense. Like, if you want as many weights as possible to be zero, then if you include the L0 norm, like the total number of non-zero elements, then that would incentivize.
With the L1 norm then. Okay.
Yeah. Okay.
But then what's the L0 scheduling then?
Not sure. Yeah.
Like, let me search scheduling.
Maybe
like, because
it is.
L1 scheduling is just when the thing where what is actually L1 scheduling? Learning rate scheduling makes sense. L1 scheduling doesn't make sense now that I think about it. We just don't change anything on the L0 and L-ing. What does figure 5? No, this is just no. They is that a typo maybe? Because figure 25 is about learning rate scheduling, and I think they might be just mistype and they make a learning rate scheduling, which makes more sense. Let me check. Okay, so And then,
They do say the same term 2 times, but yeah, it's possible.
Okay. So here they say, learning rate scheduling is, but yeah, they. Zero.
Oh no, learning rate is connected to L0. They say its learning rate is 1 over. Yeah, I mean, I think you're looking at it too.
Oh yeah, I saw that equation. They combine the classic learning rate with this L0.
They change L0 during training, right?
Well, I guess they always like compute the total amount of non-zero vectors, and that just makes the
but don't
warm-up
they
decay schedule dynamic in a way?
Some vectors to 0 at the start, right?
Yeah, that would decrease the L0.
Another vectors are not going to become 0 normally. They just get increasingly smaller and start having. If they get really, really small, they will. Normally the weights don't get to 0, right? They just get like very small float values. Right?
I really think it might be related to the pruning, because in the appendix section about pruning, they mentioned that like they train the pruning like along with task loss. It's not just like a static thing, you know? And like they have binary masks for zeroing out connections, which seems pretty related to the L. Like I think that they might have just explained it really badly, but like L0 scheduling is how the pruning works, maybe. Like if you look at page 21, it's like,
Okay.
I don't know, but they really like if that is true, I feel like they really should like connect them more.
Like my previous understanding of pruning is that it's just something they do after they train the model to just find that.
No, they say pretty clearly it's trained like with the model. Like if you look at I'm pretty sure. Yeah, look at the loss function. Although maybe I'm not so sure now, actually. We optimize our masks on a linear combination of task, cross entropy, and K, the number of non-zero elements in the mask.
Yeah, no, that sounds like they just train the mask afterwards, right?
Maybe, yeah.
That's really. Maybe we will need to look at the code for some of these things, but.
Oh, they define the L0 norm as I said it, while holding the number of non-zero parameters in parentheses L0 exactly constant. They hold it exactly constant. Wait, what?
Yes, but that's. I mean, like this scheduling. I kind of. I later going to look at Luther and Twitter and see if what people are saying about this paper. I haven't seen anything because it was. It didn't come out. It came out like last week, right? And I haven't been checking Twitter that much. I don't think people. Well, I don't see Twitter a bit. I don't think people were talking that much about this paper. Maybe Neil is posting videos lately a lot. Partly I think because he's some maths. Maybe he'll do a video on this paper and he'll understand it better than us. Or also complain about not understanding and will feel vindicated.
Oh, after each Adam V update, they zero out all but the largest magnitude entries in each weight matrix, such that every matrix has the same fraction of non-zero elements. So they enforce enforce that there's always the same fraction of non-zero elements.
Wait. So, but which elements are non-zero change then?
That's, I think, the case, because they, at every 8 MB update, they do the zeroing out
If an element,
after
this
applying
is kind
Adam
of a,
every time.
if an element is zero, can it stop being zero if you do gradient sites on it? Wouldn't it have? Don't gradient zero things? Or maybe not. Maybe I'm misunderstanding.
Maybe there's plus bias
Yeah.
that makes it non-zero.
I feel like I would need to think about this in terms of I feel like there is some math things I right now need to remember to your gradient instead. That what happens if you have a zero and you do the gradient of that matrix multiplication and if things like that. But yeah.
You need addition, yeah. Which makes sense from biases, as far as I understand.
Like if you don't have biases and multiply by like have some weight that is zero, can the weight stop being zero, or does the gradient not?
Weight matrix times input plus bias. So if the bias, so the times becomes zero, but the plus bias, if that's not non-zero, then that becomes the value. That's my understanding now.
But if we bring out the bias, if it's still zero, can it have non? Like can the gradient not be
okay.
zero? I guess it like okay. So let me think. If you had a zero and increase a bit, it could it could increase the thing. So maybe yeah. I don't know why I thought it was
Oh yeah.
theory. That doesn't make sense. Yeah. If you don't keep your weights are going to increase probably if they are all zero. I guess normally what happens if you have things like Relu and then your zero gradients don't matter because there is a non-linearity and it always maybe that was why I was slightly confused. I was thinking like normally if you have the weight to zero it's going to stay at zero because it has to increase a lot to matter for the railroad, right? Well, no, it could add to something else. Never mind. I don't know. I'm confused. I don't think I know what I'm talking about right now. Sorry. I need to review a lot of linear algebra stuff.
I think it can be changed, yeah. Through backprop.
Yeah. Anyway. Okay, I'm still confused about this, but I guess I could try to
Gradients
figure
can
out
still update it, yeah.
Like I'm still confused about what the L0 scheduling is and why these. Maybe I will have to read the whole thing instead of the jumping around like we are doing. But
it seems to me like L0 scheduling, like the way they basically just mean progressively zeroing out more weights, because they say we anneal the L0 linearly over the first 50% of training so that the model becomes sparser throughout training.
Okay.
So,
but they enforce the amount of zero.
Yeah.
That every matrix has the same fraction of non-zero elements. So they enforce it to be constant.
I think so, yeah.
Okay, I know that, but okay, that makes some sense. I was imagining the model as having some weights that are permanently zero from the start and you just train the model there. But I guess it's not that you like increase the amount of zeros for some reason. That seems like it's also kind of weird and like I wonder, wouldn't it be simple? And why not just do a model with less connections? Sure. If you want to do it efficiently, you still do matrix multiplication. But why not put zeros and freeze the zeros, right? Like put some amount of free zeros from the start and freeze those weights. Maybe you can't freeze individual weights and not the entire matrix, and the Python to make it annoying. So it turns out it's actually easier to code this thing. But conceptually, it's much simpler to just not have the connections, right?
Like it seems like the L0 is like the hyperparameter for the like how many edges can exist in the circuit. So like that's like it's like one axis on where we were like confused at the very beginning on the graph. The training loss and pruned circuit size. So yeah, I think that the L0 is one axis, the pruned circuit size, right?
Okay, so the thing the Kali is saying is that if you right, I think that makes sense. So if you initialize with some random empty connections, the connections might not make sense. Like they might not be like. It's nicer if you do the other thing because the model can decide which things to connect to each thing. And so it might want to, like, for example, like you could imagine instead doing like taking each neuron and connecting it randomly to 4 other neurons. But that makes it hard. And the model could learn to make the circuits with the connection it has, but it's better to let it pick which connections it wants, but forcing it to only have a few of them. And maybe it wants to some specific neuron have more connections or something. Yeah, okay, makes sense.
Mm-hmm.
That's almost like a super easy indicator of like important neurons. If one neuron feeds into like 20 different like non-zero other ones.
Yeah, that makes sense.
Pretty cool. I really like that. Like I feel like people don't think about complexity enough in general. Like this is just kind of like my personal thing. But I really like it. Like they kind of give like a seemingly effective way to like continuously vary the complexity almost with the L0 scheduling. It's pretty cool.
I mean, I guess normally you can also vary the scheduling by making a bigger model, which is going to be more complex. But yeah. Initializing a model with lots of interactions is one standard. Yeah. Has this not been done before? I don't know. I don't think anyone has trained sparse models in this way. Or like, I don't know any paper, previous paper. Maybe there is, but do they mention anything on? I mean, if there is some important paper about this, well, let's check the introduction in case or maybe there is a related work section and they mention related work. First encoder circuits. I mean, if not, okay, yeah. Let's check the related work, and if there is, and it's not on the related work, I will probably see people complaining about that on the internet. Smithuber saying, I made a paper about this on the 80s or whatever, and I'll mention that on the channel if I see it. But okay, let's see. Sparse encoders and circuits. Yeah, this is just the work on sparse encoders.
But do I get it correctly that the L, like in the graph, in the capability interpretability graph that we were confused at the very beginning, that the one axis is the L0, The interpretability axis is the L0 hyperparameter.
But then what's
Yeah.
the non-zero params thing?
Oh yeah, non-zero params. So
Why is this different from this then? That's why I'm confused.
okay, maybe prune circuit size correlates with the non-zero params. Then this is so confusing.
Wait, I'm dumb. I understand it. It's prune circuit size. This is the L0. This is the size of the circuits that they find with the pruning. So
Okay.
higher means that they find more bigger, more complicated circuits. I don't think that doesn't seem a bit measure interpretability because it just might mean that the model has more complicated mechanism size. And it seems like if you try a hard, I guess if it's the same task, no, but you could have the same task and you are comparing for the same task, you might still find like the bigger models or whatever have more complicated.
Yeah, that would make sense because if you look at like, you can see that the smaller models, because the other axis, the color, is another axis, which is total model size. So and you can see that the bigger ones at the very bottom, you have the non-zero params, you have it higher, and the circuit size also is lower. So like
Okay, I'm confused because
trying to formulate what I'm meaning. The relationship, like, because the amount of non-zero params, like if you have a bigger model, then you need bigger non-zero params to achieve the same sparsity, to achieve the same pruned circuit size.
Yeah, but shouldn't
And
this be
that's
a
here.
lot more sparse then, right? Like for the same size, it'd be also. Why are
That's a
they
bigger
not?
model, so
What were you saying?
yeah, that's a bigger model. Shouldn't be the other way around though.
Yeah, like it's a bit. Like, also, I'm curious why. So why is this one not? Why didn't try this one with more non-zero parameters?
Oh, it's non-zero params, not zero params. It's like the inverse of L0, or wait.
Yeah, let's say you have. Why?
No, it's not. Okay.
Shouldn't you need more? Like, why is not the? Why don't we have one with more? Like, right? This would make sense if the colors were the other way. If this was the bigger one, because then the smaller one couldn't have the biggest circle because the biggest circle wouldn't fit. But this is the biggest model, right? Is there any reason why they can't have a model? Like, okay, so if this was backwards, it would make sense to me because 10 to the 7 is so 10 to the 7 is 10 million, right? So the smallest model can't have this level number of non-zero parameters because it's bigger than the models. But this is not the smaller model, this is the biggest, right? Maybe the colors are backwards.
Maybe it's compressing the features much more, so the resulting circuit is much smaller because there is much more compression.
No. But aren't this on the? Isn't this the L0? If this is L0, why it's not? Like, why is there no, model with 10 to the 9 parameters and 14.8 million non-zero parameters?
Setting more weights to 0 reduces capability but increases interpretability. Scaling up model size shifts the frontier upwards, suggesting we can build larger models that are both capable and interpretable. Decreasing.
Wait. Shift this frontier outward. So is the colors? Wait, no. Better it's.
Making models sparser, aka decreasing the L0 norm of the weights, so decreasing the total amount of non-zero elements, while holding the total parameter count fixed, trades off the two, harming capability but improving interpretability. I wish they had a sentence about the colors as well.
Maybe is this graph not here? Maybe it's
It
more
is
appendix.
at the top.
Okay, let's go to
It's basically the same.
But maybe it has some more explanation.
Yeah,
Okay, here.
yeah.
And it's the filling color. So let's see. So more parameters there.
So more parameters equals better capability and lower
Oh yeah, scale size is
interpretability.
L0, so yeah.
And lower interpretability.
Okay, so makes sense. So the more
And
let me see.
and increasing the total amount of non-zero parameters. So decreasing the amount of zeros makes the circuit size smaller. No, it makes the circuit size bigger. And that's more
which
interpretable.
makes sense.
And circuit size being bigger is more interpretable.
Yeah, I'm not sure this is a good measure of being interpretable.
Wait, no, I think it's smaller. Smaller is more interpretable, right?
Yes.
Well,
they say smaller is more interpretable. Yeah. Because this is more interpretation. They say better on this arrow.
Here you wanna go down. You don't wanna go up.
Yeah.
Down and left. Down and left.
Yeah, it says better here. Like this corner is the best.
According
to them, I'm not convinced that this is the okay. So I think if you keep the model. Okay, so I feel like there's two variables here. Like you could have the circuit be bigger because the model is smarter and has a more complicated algorithm to the thing, right? Like thinking about the damper sample, like with Niels Groking paper, you have the memorizing algorithm and the actual modular addition algorithm. And the actual modular addition algorithm, I'm not. It might have more nodes than the memorized circuit. Well, no, actually, no. It will have less because the memorized circuit is just going to have a lot of nodes that are kind of just doing for each hard coding each chamber. Never mind. But anyway, it could be that there is some that you have a better model and you have a more complicated circuit, but it's better in some way. Like it maybe does more things. And so it increases the size without, and there is not a problem with interpretability. It's just the actual circuit. The actual thing is just more complicated.
Actually, like increasing the model size decreases the pruned circuit size.
That's really counterintuitive to me, actually. Like it's almost like bigger models, like they learn. Like I'm not sure how this factors into like memory, but it's like because I think this is given a certain task, like they print it for that task,
Yeah.
So it's like given.
We can go to the here how they.
There's more compression in the bigger models, so the circuits are smaller.
Exactly. Yeah. Huh.
Yeah, it makes sense. The circuits are okay. So then it makes sense. So then it's more the opposite thing where the bigger models are finding simpler ways to do things. Like they are going from memorizing to having actual algorithms for the simple tasks. At the same time, yeah, you need to hold the law check. You told to take into account to the laws because you could have a simpler model. I wouldn't be surprised. The thing is that on this task, all of the models can do the task because it's very simple. But maybe there's some more complicated tasks where you have a better model that has lower loss, but is slightly more complicated because it's doing more things and the original model just didn't do the task correctly, so it didn't even have that circuit completely or whatever. I don't know.
Yeah, I can see that there might be edge cases, but right now on this task, it seems like they figured out this, in a way, general law, the scaling law of in all those axes. And I wonder, did they ask, I think, in the conclusion or somewhere in the blog post, maybe like they don't know how it generalizes to other tasks and bigger models. So that's, I guess, open question. Yeah, this reminds me of the whole like how people think deep learning will go before deep learning took off, of like that it will just overfit by default, but actually in reality it seems like this is the counterexample. Another one.
Yeah, I mean, the difference is that, like, again, I was starting to argue earlier with the Neil thing, but I did realize in the middle that actually the prune circuit size on the grokking task probably goes down as the model learns the actual algorithm. Even if some more abstract sense is less is more complicated because the other thing is just memorizing a bunch of things. But yeah, you need a lot of you probably need a lot of nodes to memorize a lot of things.
You need more you need more bits for memorization since everything else is in a way of compression. Then yeah. I guess not sure how general that is. Yeah.
There seems like it will be edge cases, but like where like you will expect better models to have like for the same thing a simpler circuit or whatever, but if you are testing a task, it might be used and you don't check that you have the same performance. The thing I was saying, you could have two circuits, one that's more complicated, but grain descent still like is more because it gets a lot lower loss.
Shortcut learning as well.
Oh yeah, so the thing the car says, she mentions about sparse attention, but I think there are a lot of papers that do sparse attention for optimization lists. There's a whole pile of people trying to find these ways to do attention sparsely, but that's not the same thing. They are not doing zeros on weights, right? I think they just put the normal sparse attention thing. They are not calculating some attention values instead of some parts of the weight matrix or whatever, and that's just if you have very long context to to not spend as much compute on that. Like, I don't know, there is like flash attention, all the stuff. I think it's that, right? Well,
yeah.
I haven't actually sent the paper. Let me check the papers the cat sent, but sparse transformers. Yeah, I don't not sure of this, but I have the impression this is like sparsity on the attention scores, not on the weights or whatever.
And here they just care about the weights.
The pruning thing. This also is pruning. Let me put them here. So there's also this pruning thing. No idea.
I haven't really looked at those papers yet, so it just seemed like they were like I'm just interested in the idea of like sparsifying as you train. It seems like that's what they were doing.
Yeah, after Achyuta V, they do the sparsification.
I guess people weren't. Maybe people did these things already, but they were trying to make inference more efficient. They weren't trying to do something like make it more interpretable. It seems like it's probably like the idea of let's train a network that's sparse for interpretability might be new. And in some sense, it seems like an obvious idea, but doing sparse encoders was also an obvious idea, and it took a while for people to think of it. So, and in this case, people might not have thought about it until right now. So, yeah, they don't. They talk about this. Oh, there is sparse weight training section. Wait. Okay, so so this saying that there are papers for sparse training. They might not have been done for interpretability. I guess we will have to. Let me go back to the thing. Let's go to this face thing. Oh. I don't know that I have to. Yeah, well, all papers. It's funny that papers from 2018 in AI are extremely old now. Yeah, this seems like people were trying to do sparsity for other reasons. Because they were doing things like, brains are sparse. They were trying to do it for optimization reasons.
Like there's this. I remember some papers saying like that you can remove most of the weights and still don't lose performance really.
Yeah, and there is like, I mean, people these days, ChatGPT models are using mixture of experts some way. So like,
that's another thing.
Papers training, like there's a lot of stuff in the literature of training sparse models. I don't know if there is a lot of things about this specific way of doing sparse models. How much? Maybe all of this overcomplication is from there is some previous literature that was training sparse models for optimization reasons, and they are copying some ideas, and that's maybe how we didn't explain that, but they didn't make that very clear. If so, but anyway, I think the novel part might be, apart from the specific details, that they did it for interpretability and then did the pruning thing and found things. The same way that it's not like dictionary learning was a new problem or people haven't done the sparse autoencoders for other things that aren't interpretability before. It's just that people thought of using it for interpretability. Yeah. Anything else, or do we?
That's still the curious question. Like it seems like now, at least in the open source space, and seems like it's a bit leaking from the frontier labs as well. It's like since they are basically a mixture of experts models, that like the total amount of parameters seems to be increasing again, but the active parameters, like in the mixture of experts, seems to be like the ratio between the active parameters and the total parameters seems to be increasing. Therefore, like you have DeepSeek with 500 billion parameters and 32 billion active parameters. And then you have Kimi K2 with like, which is twice as big, but the active parameters is the same amount. So I wonder how that affects circuit sparsity as well.
Yeah, I do expect.
Yeah.
I don't think. I doubt this kind of model is going to be competitive anyway. Like,
It's
Yeah,
also interesting.
like
I think like for MOE models, do you guys know about? There's some empirical law where it's like square root of total parameters times active parameters is like supposed to be approximately equivalent to like a dense of the same size. But yeah, I don't think it's too related to like interpretability, sparsification. But it is kind of interesting. It's like I think sparsification can be good for capability and interpretability.
I mean, it would be nice if it worked that it turns out that there is some kind of sparsity that works for capability and also happens to make it more interpretable. Yeah, I don't think that's what they were going for here, and I yeah I doubt this kind of method doesn't seem like it will actually. I mean, it does. The loss does get a lot worse, right?
yeah,
As you
improving capability improving interpretability this way in this paper is harming the capability basically.
Yeah.
I mean,
Though I like I still wonder in the future if you could like
I mean, that's not necessarily
maybe
the case that the okay. So mixture of experts, I'm not sure, but it wouldn't be surprised also has capabilities with respect to having a model that size, fully connected. It's just that it's cheaper. That such that it's more cheaper than the amount of capabilities you lose. So you can train bigger models with Mr. Peppers or whatever, and that works
yeah.
better than training or
So
smaller. Yeah.
overall you get more capability per dollar basically.
Yes. And I would be surprised if this thing where you put zeros on things also increases capabilities per dollar. Also because it's not as easy to there is no nice way of running it cheaper. There's probably some mathy way of doing it later, but it's not as obvious how you still have to do the matrix multiplication even if it has zeros. There's probably some math trick to simplify that. Then thinking about it, but
Yeah.
but
Probably not by too much though. It's like, yeah. Yeah, no, like I agree that this method is not seems good for capability. I mean, because like even if you can simplify it somewhat, it's just not built for it. It's like, zeroing out weights is just not. But I really do think that like I really like that this paper uses the signal of like complexity of the model in some way. Like I feel like it seems like a key to capability and interpretability to me. It's because like overfitting is because the model is too big, right? Or it's like the model, it has too much space to shove crap, right? And like I think minimizing the complexity of the function seems like a really very straightforward way to both improve capability because you're actually finding like a simpler function. And then
normally people do a L1 norm penalty on the loss anyway. So they are trying to minimize the complexity that way.
Yeah, I know about different methods of regularization, but it just doesn't. It seems like it's still like the same architecture, and I'm just not confident that applying that to some latent vector is like enough.
I mean, putting things to zero. People were doing dropout. We was already putting things to zero randomly, right? Although it was not the same because they later removed the mask. And people stopped using dropout because it was not very good, but maybe that's because it was not that way. Maybe it turns out doing this zero thing actually helps in some way. It turns out to be super good for capabilities or something that would be weird.
People aren't doing it because it's harming the capability, right?
Yeah, I think dropout wasn't working very well, and people just stopped doing it because it was worse than doing other stuff that people are doing now.
It's interesting though, like dropout and like L1 regularization, those are like keeping the architecture constant. I mean, like, okay, dropout maybe is not exactly, but like, this kind of thing seems like it's much. I don't know. It's much closer to to modifying the actual architecture. You know, it's
I
still
don't
like,
know,
you know,
it feels like maybe it's doing the same, like it's changing things. It's just changing things in a way that looks more intuitive to you. But the L1 penetration is still making the weights smaller, which means you can fit less info on them because you have less bytes for that or whatever. So, like in some mathy way, you could reshape, think of the model in some other way, which is basically also putting some things to zero or something. Uh, I don't know.
Yeah, it's making it smaller but not zero. Yeah.
Also, yeah, the cat is saying his there.
But yeah,
So
at the same time, they train to keep the amount of zeros constant. At the same time, in pruning, they do another, like deleting subset of nodes by mean ablation. That's interesting that they have like those two steps in a way. And when exactly is pruning applied? After yeah, that's applied to get the sparse circuits. Okay. So at training, you have this constant amount of zeros in. And is it applied to like each layer or the whole model? So like, is the constant amount of zeros in each layer?
you mean
That
absolute
will be
K?
equivalent. I think so. I forgot how that was defined.
They
Oh.
did say for absolute top K, they keep 1/4 is the value of non-zero, which means, you know, 0.75 is the value of zero, and I think that is specific to each layer. Yeah, like even I think they even say that the Q, K, and V matrices as like separate things. Like even each of those, it's like the same operation applied to each of those.
But they changed this amount in the graph we looked at, for example. So that's like another.
Oh wait, so you mean on the graph the like yeah, where it says like 2 to the 10 or like 2 to the 9?
Oh yeah. Oh yeah, okay. So, since that's one number like this, the L0,
I think
I
those
mean,
are
not 2 to the 10,
gotcha.
etc. But the L0 at the sizes of the points.
Yeah, I
So
think they're
like,
just two separate things, I guess. I kind of wish it seems like they almost have 3 or 4 different ideas here to sparsify, but they don't really make it clear that they're like separate things.
yeah.
Sorry, which things which I was not paying attention?
Say again.
Sorry, I was not paying attention. What are the 3 ideas you were talking about?
Yeah,
Well,
so
they
there's
have
this.
yeah, you go ahead.
Or okay. Well, you might know it better, but yeah, like there's this L0, which is like the total amount of zeros across the whole model, if I understand correctly. Then there's this pruning method, which is like when you are getting the sizes of the pruned circuits, then you mean ablate under some that
Okay,
are.
but the prune thing, I think is separate because it's not the sparsity on the model. It's a separate method that they do on the model to find circuits.
So
Like
I think
it's something like circuit search instead of making the model sparser.
I think that the L0, the pruning, and the absolute top K are 3 separate things that are not even super closely related. I think it's like they have 3 things.
Okay, but I think okay. So to me, I feel like they have 2 things on the model, and the prune thing is what they use to test that their method works. Because they think that's actually trying to so I feel like the L0 and the top K are the ways they make the model sparse, and the pruning is the interpretability technique that try to use to show, okay, we can interpret this model and show that this has this circuit that does addition or whatever.
Yeah, I think that sounds right to me.
Like the other things are part of the model well, part of the training of the model. One is part of the top case, part of the architecture. The L0 is part of the training, and the pruning is some extra thing they do with the train model on some specific tasks to try to find. And they have a they say that later that have a date set of like 20 tasks, and I think this is just the mean of the size of those sequences for those tasks.
Actually, maybe they did explain it some, because even on the very first page, it shows they have two main steps of train it sparsely and then find the circuit. So I think, yeah, like you said,
Yeah.
it's like the L0 and absolute top K are in step 1, and then the pruning is in step 2.
Yes.
Makes sense, yeah.
Like this is like, for example, like Anthropic trained the models, however they trained the models, and they did those sparse encoders, and then they did the thing where they find circuits on those sparse encoders and do supernodes, whatever, or all that.
Although
Yeah,
it does
yeah.
seem like in step 1 they're training general. Well, okay, I mean, I guess finding a circuit is the same as like kind of.
Anyway, I sure you.
Huh. Finding a circuit is just the pruning and just taking and just then looking at what it corresponds to the different activations, I guess.
It's almost
It's
like the pruning is the same thing as like, I mean, I guess it's the same thing as figuring out like the tiny task specific model, I mean, yeah, I mean that's literally just the same thing. But in step 1, they're training general model.
Yeah, it's like in a way similar to when you do the pruning before you do attribution graphs, and then you try to interpret that attribution graphs. But one thing that comes to mind here is that they are just connecting layer I with layer I in the other model. Therefore, this is just like equivalent to sparse autoencoders essentially. Well, in a sense, since it's just one layer interpreting another layer, or like correspondence, like on just this one layer level. But like cross layer transcoders are like across many layers. Therefore, I would say maybe next step for them that they might try to do is try to make the sparse model connected to many layers in the dense model. I'm not sure though if like in those cross-layer transcoders.
I think what they're trying to do is the sparse model. They're still trying to keep it like the same function, basically just sparse. Which that seems like a little bit different from like cross-layer transcoders. Although, I mean, maybe I don't know.
I thought I had accidentally closed the recording because I closed my connection to accidentally the window where I was connected to the Oracle machine where I doing the recording,
it's on
but
YouTube?
it was still recording. Yeah, it's still on YouTube. Still streaming on YouTube. I was scared for a moment because I accidentally closed the window, but since it's in a Oracle machine, to prevent that kind of thing, it just keep recording, and okay, it's fixed now.
Yeah. So since on YouTube you have to click on end stream to actually end it.
Yeah,
but
I just had to relog on the thing to be able to stop OBS when we want to stop. But yeah, let's keep going if people want to. I mean, it's kind of late, but
I mean, if you want, there's a Twitter thread on the paper. We can summarize it there and see if we think that's true what they say in the Twitter thread.
We could do that, and I guess we could and yeah. Also, someone is calling me down there. So wait a moment. I have to go. Someone is calling to my door. I'll be back in a moment.
Okay. Yeah. I do wonder what would change if they did the cross-layer transcoder approach. Yeah, it would be different, I guess. They are. Well, it would. Like you could model the different interactions between the different features more. since you have the contribution from the different layers. But yeah, since you're not only reconstructing, but you're also the dense model, but you're also taking into account the overall loss, then that's different then.
Sorry, I'm back.
Okay.
Just that Alex is here because he wants to help me mount my new computer, and yeah, he didn't expect me to still be on the reading group at this time. But let's finish this.
Okay. Alex from Mech Interp. Okay, yeah.
Yeah, he's the other admin in the server. He doesn't really do Mech Interp. He's mostly I made him an admin because he wanted to help me with the Discord and stuff. But yeah.
Okay.
Anyway, so yeah, we were going to look at the Twitter thread. Obviously, the most important part of the paper.
It's in a way a consolidation, I think is the word.
I mean, most of the people are just going to read of the Twitter thread anyway.
Yeah.
I don't remember who. I think it was. I don't remember who it was. Maybe it was Max Selgris that said that you should spend as much time on the three main parts of the paper: the Twitter thread, the abstract, and the rest of the paper. Excited to share your latest work containing language models. Okay, yeah, whatever.
Do they say anywhere in the paper if they apply the pruning algorithm to models that were not trained in their sparse way? That seems to be interesting. Like I bet the results would be much worse.
Pruning algorithm.
Yeah,
right.
Like if they train the same size model but just without the L0 and the absolute top K, I bet it would. I mean, I'm sure it would be like much worse. Maybe even just like totally fail.
I'm curious if you look at this. So the where was the yeah, this thing. So I wonder if these lines just kind of extend into the full model size, right? Well, maybe they do actually. This kind of okay. So if this is 10 to the 7 and this is 10 million, so like is so this one is almost the full model, right? If I understand correctly, because it's like
that's the smallest one. The total parameter count is 10 to the 7.
Yeah, that's 10 millions, right? 10 million parameters, right?
Yeah.
So if this ball is 3 millions, that's like, not the entire model, but like 1/3 of the model or something.
The visualization is like hilariously bad. Like using the circle sizes when they could have used like X's and like squares or something. Like, come on,
you
guys.
shouldn't put 4 variables in the same plot.
Yeah.
Just make 4-dimensional graph.
Yeah.
Or multiple charts. Yeah.
Or like if they just like change the circles into like X's, because they aren't trying to represent like a continuous thing really. It's like they have like 5 different categories, but like
they also should put why not use different shapes. I tried to like here. I was trying to figure out which of these circles is this one. It's really bad. People normally just make one a triangle, one a square, and another a circle or whatever.
This paper in general, it's like surprisingly rushed. I feel like I wonder if there was some like I don't know, internal thing like pushing them to publish something.
Anthropic releasing so many papers. Come on, we have to also release something
Yeah.
to get the laugh from the Mech Interp community.
You know what? This is maybe too. But what if they are going to? I don't know. I feel like last time some people published a paper like this. It was the super alignment thing, and it ceased to exist soon after.
Yeah.
I hope it's not. This doesn't mean that they are going to stop doing interpretability at OpenAI or whatever, and they are trying to rush the paper before they get muted or something. I doubt that, but I don't know.
It seems like
Maybe
OpenAI has
Anthropic
started.
is.
It seems like they've started caring a little bit more about Interp recently, but it's hard to say. Yeah.
Let's go. I mean, I know Leo Gao specifically has always kind of has published other things, but yeah, I don't know. Secrets are made. Okay, let's read the Twitter thread. Our secrets are made of literal weight entries that can run on isolation and be directly interpreted. For example, the secret that closes Python strings uses two member cleaners and certifications. Yeah. Yeah, the thing is, so the pruning, by the way, is to make these circuits. It's not something to make the model more sparse. It's just to the way generate these circuits and plots and whatever.
Yeah.
And then you do some like human like circuit tracing basically on top of that.
You get the circuit. I think you get this graph, and you have some human trying to figure out what the parts of the graph mean. Yeah.
Although
Just
compared to like the Anthropic circuits, this looks like it has way less elements, and it looks like it'd be somewhat easier to.
Seems much easier than doing the Anthropic thing. And even the topic time, there is a way to automate it. Is you ask ChatGPT to do it, and then use other examples on the task to grade it and see if the things that it said will activate for some things will activate.
Yeah, but people tried using LLMs to just create attribution graphs, but that's not good enough. So people are finding different
the
ways.
other thing that I would say was also not that good. Humans are better; it's just cheaper.
Yeah.
But yeah, I mean, I guess you can make something like Europe if this gets popular and it actually works. Which I mean, it also seems this seems very cool, but at the same time, it would be that surprising if, like, in a year nobody remembers this paper because it turned out to not really work. I just be a cool demo of something that really took off. But if it does took off, you could imagine having this on Neuropedia and people manually trying to understand them.
Yeah.
I guess it's like, did they mention also, like, does the L0 and absolute top K, did they mention how that affects performance? Because pruning obviously is going to kill performance on anything that you're not pruning for, but I don't know if they mentioned like what the first stage does to performance versus like not having it. Maybe it's a fun experiment to try.
The top
I was
K,
saying, yeah, like the top K and the L0 scheduling.
Okay, so the L0 scheduling, I guess it implicitly. So the L0 here is the final L0, but I guess it's enforced. It should be the same. So the L0 is basically already this graph, right? It's in this plot, right?
Also, one thing we missed in the paper, they are doing feature steering, and it's consistent and it works.
Oh, nice. But yeah, I feel like this paper. I feel like the paper is too big to do one day, and we just. We started, we got to the method session, then saw the bridge thing and got stuck there for like an hour. But I don't think we ever even got to read the all the results section or even the conclusions.
Yeah, the steering is at page 7, 8. I mean, yeah, here.
I mean, maybe even if we don't get to Leo, we could just some other day, probably with some other a break with for other papers in the middle, try reading a bit more of it or something. I don't know, like for the Anthropic paper. But yeah. Anyway,
Yeah.
let's look at the Twitter thread maybe as a summary. Oh yeah, that's also nice. Another thing that's in the paper and I hadn't seen. There is apparently they find an adversarial attack that they would have thought otherwise for the nested attacks, the nested, yeah, list thing. Yeah, they also think it's unlikely the level scale to frontier scale. Once they know for interpret the GPT-3. That would be really cool. Like, even if they never scale to frontier scale, they don't have to. It's having a fully interpretable, like a much better, not I think fully interpretable. It's probably still not as easy as just looking at it. But saying easier to interpret GPT-3 could be will be huge. Maybe that actually is too optimistic or something.
Yeah. They also mentioned that they still measure polysemanticity in the circuits.
Yeah, anyway, so I guess we could leave it here. It's been like a lot of hours now. Maybe we can continue another day. But yeah. Does anyone has anything else to say, or do we just end it here? If you want to keep talking, I might leave and you can talk to each other, whatever.
I think we pretty much covered the important parts.
Yeah.
Yeah.
Makes sense. I will miss a lot of things, but yeah, we will have to go the day.
It's a very dense paper, yeah.
Yeah. I'll stop the recording.
I'm just skimming the rest of the paper to see if